In this video, I want to derive a result that I will use in the following lectures. We want to prove the following relation. So we have I will define I as an integral. It's an integral from minus infinity to plus infinity of e to the ax divided by 1 plus e to the x dx. And now here, if you make a substitution of the following kind, v equal to e to the x, you can easily show that this is equal to the integral from 0 to infinity of v to the a minus 1 divided by 1 plus v dv. And we will prove that this result, the integral is pi divided by sine of pi a. And here we assume that a is a constant in the interval 0, 1. So it cannot be equal to 0 and it cannot be equal to 1. So the outer values of this interval are excluded from the values that a can take. And we want to prove this result, so this equality here, in particular this one, because this one here is trivial, it is just a substitution. But as I said, this is a result that we will use also in the following lectures. So I want to derive this result. I want to start from this one, and then I will show you why this result is important, because we will derive some properties related to the gamma function. Anyway, we will consider now the integral along a contour, and we have the integrand of the following kind: e to the a z, so in this case z is a complex variable, 1 plus e to the z in the denominator dz, and we are going to integrate along a contour that I'm going to call C sub r, CR. And C sub r is the following contour, so it's going to be very easy to understand. Let me try to draw the imaginary axis. Here we have the real axis, and I am going to define this point along the z-axis to be r, capital R, and we will let r go to infinity in the following. But for now, it is a real constant on the x-axis. Then we have another vertex here of a rectangle. So I'm going to define a rectangle like this. This vertex is minus r, this vertex here is r plus 2 pi I, so the imaginary part of this vertex is 2 pi, so we have 2 pi I here, and of course this one will be minus r plus 2 pi I, and we are going to define it in such a way that we are going to travel along this contour in a counterclockwise manner. Now, if you take a look at the integrand here, this integrand is going to be equal to, infinity. We're going to get a pole when this denominator is going to be 0. And the denominator is 0 when e to the z is equal to minus 1. And this means that z is equal to pi I, right? Because if z is equal to pi I, we get minus 1. So we have a pole somewhere here, right? This is pi I. Okay, and now by knowing this, we can apply the residue theorem to this contour. So let me erase this part, and I'm going to write it here. So this integral will be equal to 2 pi I times the residue of this integrand, so e to the az divided by 1 plus e to the z, and we have to evaluate the residue at z equal to I pi, like this. So how do we do that? It's quite easy, because we have a very simple pole there. So we take the integrand e to the az divided by 1 plus e to the z, we multiply by z minus I pi, and then we take a limit. So in this case, we take a limit as z goes to I pi. Simple as that, right? So you can see that when z goes to I pi, I mean, here we have a 0, and also here we have a 0. So we can use the L'Hopital rule. So we have 2 pi I. Here we can evaluate this exponential already at I pi. So we have a I pi, and then we have 1 divided by e to the z from below. So I have taken, basically I have taken a derivative of the numerator with respect to z and also of this denominator with respect to z. I'm applying the L'Hopital rule to this part of this function here. So when you evaluate z at I pi, here you can cancel this z and you can put I pi. And of course, e to the I pi is equal to minus 1, so we get minus 2 pi I. E to the I a pi or a I pi, something like this. Okay, you can write it in this fashion. Now we are going to define. I'm going to define I sub r as the following integral. So integral from minus r to r e to the ax divided by 1 plus e to the x dx. So basically it's this integral here performed along this horizontal line on the x-axis. This is IR, right? And we can also define I prime r, I prime sub r. It is the analogous integral, but it is performed over the top side of this rectangle here. So I prime sub r is an integral performed over this top side of the rectangle. And now this is equal to the integral from r to minus r, because we are starting from this vertex and we are going over to this vertex here. So from r to minus r, and then we can write it as e to the ax times e to the a 2 pi I, because remember that now our variable, our generic variable which describes the points along this top side is x plus 2 pi I, right? Because 2 pi I is the ordinate of these points on the imaginary plane. These points here are described by these imaginary parts, right? So we can write it like this, and then we divide by 1 plus e to the x times e to the 2 pi I, but e to the 2 pi I is of course equal to 1. And then here we have dx, like this. So if you change the order of integration, so if you want to go from minus r to capital R, here you have a minus sign. Then you can put this e to the a 2 pi I out of the integral, and then you are left with the I sub r. So I prime r is proportional to I sub r in this fashion. And then you also have the integrals. You have two integrals on the vertical sides, this one and this one. For example, let's consider the right vertical side, so this one here, and I'm going to integrate over the vertical side, and let's assume that we call the vertical side a sub r. So we are going to integrate over a sub r. We have the integrand, which is e to the az divided by 1 plus e to the z dz. And let's consider the absolute value, the magnitude of this. And remember that now we can, so if we want to parameterize this vertical side, we can set z equal to r plus it, where t spans all the points on the vertical side. We have to integrate from 0 to 2 pi. It's quite easy to see that. So we have to take the magnitude of this. We have e to the AR, then we have e to the IAT, and then we divide by 1 plus e to the R, e to the IT, IDT. And then this is less than or equal to. So now we can take this magnitude and we can put it inside the integral. So we know that there is a very simple theorem in mathematics that tells you that if you take this magnitude and you put it inside the integral, you can use this symbol. So you have less than or equal to, and then you have integral from 0 to 2 pi, and then you take the magnitude inside. And when you take the magnitude inside, you can take the magnitude of the numerator and also the magnitude of the denominator. When you take the magnitude of the numerator, you have this complex exponential whose magnitude is equal to 1. And the same the same holds for I, so the magnitude of I is equal to 1. So you can write e to the AR in the numerator, which is something positive or greater than or equal to 0, and then you take the magnitude of the denominator. So you can write it as 1 plus e to the R, e to the IT, dt. You can write it like this. And then, of course, you can also rewrite, if you want, this magnitude here. So this magnitude can be written as you have e to the R cosine t plus 1 squared plus e to the R sine t squared, and then you take the square root of this. And if you want, you can also rewrite this magnitude as e to the 2r, because you have cosine squared plus sine squared, which multiply e to the 2r when you raise it to the second power. And then you have plus 2 e to the r cosine t plus 1 raised to the 1 half. And you can also simplify this, so you can take out of the square root e to the 2r, so you will have e to the r, and then you get 1 plus 2 e to the minus r cosine t plus e to the minus 2r, let me write it properly, e to the minus 2r, and then you raise it to the power 1 half, like this. When you let r go to infinity, you can see that what's inside the square root will go to 1, because e to the minus r will go to 0, as well as this one, so you will get something which will become closer and closer to 1. Then if you take this e to the r and you put it in the numerator here, you will have e to the a minus 1 r. And if you remember, a is a constant between 0 and 1, which cannot be equal to 0, and it cannot be equal to 1 either. So this exponential can be written as e to the minus mode of 1 minus a r. 1 minus a is positive, so I can also eliminate this mode or magnitude. So you can see that this will go to 0 as r goes to infinity. It's quite easy to see. And therefore, due to these considerations, you can see that the integral along the vertical line, the vertical side of the rectangle, this integral will go to 0. And the same holds for the left vertical side. It will also go to 0. Now, if you let r go to infinity, you can see that when r goes to infinity, I sub r will go to I as r goes to infinity. And we defined I in here. It's quite easy to see. So basically our equation, and I'm talking about this one here, remember that we have this contour integration equal to minus 2 pi I e to the I pi. So you only have two contributions along the contour, which are I, so the integral along the bottom side of the rectangle, so it's the horizontal side at the bottom. And then you have minus e to the 2 pi I a, and then this multiplies I, which is equal to minus 2 pi I e to the a pi I. So you can solve for I, and you get I equal to minus 2 pi I e to the a pi I divided by 1 minus e to the 2 pi I a. Now you can divide by e to the a pi I both the numerator and the denominator. And you can also divide by 2i. So we can write this as minus pi divided by e to the minus a pi I, and then we have minus e to the a pi I, and then we divide this by 2i. So we can write it exactly in this form. Here in the denominator, now you should be able to recognize it's minus the sign of a pi. So here you get pi divided by the sign of a pi, like this. And this is the result that we get, and we will also use it in the following videos.